Hello everyone. In today's class, we are going to see the analysis of Class A power amplifier. We know that the Class A amplifiers can be classified into two. One is directly coupled Class A power amplifier and other one is transformer coupled Class A power amplifier. As name itself indicates, in direct coupled type Class A power amplifier, we are going to connect the load RL directly to the collector. Whereas when we connect the transformer coupled type, the load is this load is coupled to the collector using a transformer called an output transformer. So now here as you can see this RC, which is nothing but your load, is directly connected to the collector terminal. We are going to call it as direct coupled class A power amplifier. This circuit is a simple fixed bias circuit wherein the RB value is selected in a such a way that the operating point of this transistor will be in the middle of the active region so that the output is obtained for entire duration of the input cycle. So that's why we are calling it as series fed directly coupled class A power amplifier. Why class A? Because you have selected your RB such that Q point is in the center of the load line. Why directly coupled? Because load is directly connected to the collector terminal or collector in the circuit. Now, let us do the analysis of this class A power amp. For that, very first thing which we have to do is we are going to have the DC equivalent circuit of it. Having the DC equivalent of any circuit means we are going to remove the AC power supplies, and because of that, this as there is a no AC supply, the capacitor will be an open circuit and your circuit will remain so. What is that? Your Vs is gone, C1 is open. So what you can see in your circuit is DC supply, RB, RC, a transistor. RB, RC, DC source and this transistor. Now to do the analysis, that means to find out the different parameters of your class A power amplifier, let us apply the KVL at the output side of this power amplifier. So now you can see here, if I apply the KVL at the output side, Kirchhoff's voltage law at the output side, what we are going to get is VCC minus ICRC minus VC equals to 0, right? Same thing I have written here, VCC minus ICRL minus VC equals to 0. Now as we are interested to find out the collector current, let us take this ICRL outside and make these terms as a VCC minus VCE. So from that we are going to separate it out, this IC equals to VCC by RL minus 1 by RL into VC. Let us say this is called it as equation number 1. Now we are going to compare this equation 1 with a straight line equation. What is our straight line equation? Y equals to mx plus c, right? Where m is your slope. Now, if I compare this equation with this, what I can see, my y is equals to ic. My constant is VCC by RL, that is c, and this is my slope, that is m, that is 1 by RL, and your x is my VC. That means when I compare the collector current equation from the fixed bias class A power amplifier and compare with the straight line equation, these are my parameters obtained. Now, in the next step, why I'm going to get that? Because I want to find out the DC load line for that circuit. Now, in this equation, let us put the IC equals to 0 and then second DC equals to 0 and try to find out the coordinates by putting IC equals to 0 in the previous equation. We are going to get the coordinates as VCC equals to VCE and your IC is 0. That means the coordinates are VCC comma 0. The same way you put the VC equals to 0 in equation 1, we are going to get the coordinates as 0 and VCC by RC. That means VCE and IC is nothing but VCC and 0 here, and here again VCE and IC. VCE is 0 here and IC is VCC by RC. Now, when we are getting these coordinates, we are going to plot these coordinates on the output characteristics of a transistor. Now, you can see this is my output characteristics of a transistor, of a common emitter transistor, wherein VC is my voltage and IC is my current. Now, these are the output characteristics of a transistor with the different IBs, IB5, IB10, IB20, IB30, IB50 microamps and so on. Now, I'm going to have this plot these coordinates on the x and y axis and join those 2 points with a slope of minus 1 by RC, and where this line cuts your output characteristics of a transistor, there I am having my operating points. So in that way you can see this is my VCC comma 0. So this is VCC 0 and 0 VCC by RC, 0 VCC by RC. Now this and these 2 points I got. Now I'm going to join these 2 points, and now this is what my DC load line is. Now where this DC load line cuts my transistor output characteristics, there I'm going to have my operating points. Now you can see here is my operating point, here is my one operating point, here is one, here is another. Like this I'm having different operating points. Now choice is ours where we are going to select our operating point. And as we know that we are going for class A power amplifier, we are going to have our operating point in the middle of the active region. So this is what my operating point is. This is my operating voltage VCQ and this is my operating voltage ICUQ. This Q indicates that there is a operating point current, operating point voltages. After having this output current equation, let us do the DC analysis for the same circuit. Now, we want to know what is the base current and what is relationship between the output current and output voltages. So now if we apply the KVL at the input side, what we are going to get is VCC minus IBR minus VBE equals to 0. So from that, VCC minus IBRB minus VB equals to 0. Let us take out the IB to the left hand side, and to rearrange the equation we are going to get the relation of base current is nothing but the the DC voltage minus base emitter voltage is zero point 0.7 divided by the base resistance, that is the R. That means this is what my I when I do the DC operation, I got my IBQ as VCC minus VBE divided by R. And we know that ICQ is nothing but beta times of IBQ for a common emitter transistor. So I can write that as ICQ equals to beta times of, when I know IB and IC, and from the KVL at the output side, I got my VCQ as VCC minus ICQ into RL. Now in the next point, what we have to do is we have to see the DC power. DC power. Why we want all this? Because we want the efficiency to be get calculated, and the formula for efficiency is AC AC power divided by DC power. First we are going to get DC power, and then we are going to get AC power, and then we'll equate these two. So now we know that the DC input power will be get provided by the DC power supply. That means when we don't give any AC input signal, the DC current drawn is the collector bias current, and that is represented as a IC. Therefore, what is the DC input power is? You know that power is nothing but V into I. What is V? Which you have applied the DC voltage. What DC voltage we applied is VCC, and because of that we got ICQ. So VCC into ICQ gives me a DC input power. That means the main important point to be noted here is, even though if your AC input signal is applied, okay, whatever the average current drawn from the DC supply remains same.